Hey guys, just thought maybe I'd stream a little bit of doing some of the homework for this class. So I've been going through this class a little bit. I'm on week 3, I think. The homeworks, the assignments. So just hold on a second. All right, so let's check it out. So yeah, so we got the assignment. And we got the solutions. So let's check it out. Assignment. So I was looking at, so I did start on the first question. So we can just kind of go through it a little bit. It's the best way to do this. All right, so here's what we got. I wonder where I can kind of draw, like what would be a good way to kind of have this up over here maybe? Like I'll have text edit. I want something with a white background. Could just have like a blank PDF. Let's see. If the last page is kind of blank, can kind of do that. Let's see. What if we had both of these open? I wonder if going side by side would be good. Maybe. Might be okay. I'll try it out. Let's see. All right. So the hats of N. N persons thrown into a box. Persons pick their hats at random. Okay. It's the problem that every person gets his or her hat back. So N persons, N hats are thrown into a box. So you got kind of like, got a bunch of hats that get thrown into here. We say, every person gets his own hat back. So I was thinking about this, like you can kind of start simple. Like you can say that N is equal to 3. And let's just do it for the case where N is equal to 3. So in that case, the first person kind of think of this as a sequential decision process. So, like, I don't know, if you just kind of like do out the math, it's like, oh, there's a 1/3 chance the first person gets their hat back, and then there's only two hats left, so there's like a 1/2 chance that the next person gets their hat back, and then given this, there's like the third person goes, like they're definitely gonna get their hat back. So it's like 1/3 factorial, and yeah, I mean that's it. It's kind of thinking of this as a sequential decision process a little bit. So you have like, so there's like a 1/3 chance the person pulls out their hat. There's a 2/3 chance that they don't. So this is kind of like the good path, and then this is kind of like the bad path. So this is like the first person, and then in this branch, the person got their hat back. So there's only two hats left. So the second person is going to be like, all right, there's a 1/2 chance they get their hat back, and there's a 1/2 chance that they don't. So yeah, this is the good branch. This is the bad branch. This is like the second person. And now, so I don't know, maybe down here we can say there's like 3 hats. And down here there's like 2 hats like remaining. 2 hats remaining. And now there's only 1 hat remaining. And so, yeah, in either branch, like, well, I guess like in this branch, yeah, it's going to be good. Just like 1 out of 1 chance. And like down in this branch, there's the wrong hat remaining. So there's, I don't know, I guess it's more like this. It's like there's 100% chance that they get their hat, and there's a 0% chance that they don't. Down here, there's like a 0% chance that they get it, and there's a 1%, there's a 100% chance that they don't. Wait, there's oh yeah, yeah, so these are just flipped. So yeah, so I guess kind of like 1A, the chance that every person gets his hat back, yeah, it's like 1/n factorial. And we can look, oh nice, it's just this annotation thing here. That's great. Is that always there? Yeah, it's like it's always there. Cool. Let's look at the solutions. Yeah, 1/n factorial. Consider the sample space, all possible hat assignments. It has n elements. The sample space of all possible hat assignments. All possible hat assignments. Okay, the sample space of all possible hat assignments, that would kind of look like, all right, so if we had 3 people, then all possible hat assignments are like, they're like, they kind of all look like this, where it's like, I don't know, the first person gets, hat 3 1, second person gets hat 2 back, third person gets 1. There's like another one where it's like 2 3 1. There's another one where it's like 1 2 3. There's another one where it's like 2 1 3. So it's kind of like this. So the sample space of all possible hat assignments, it's like we have like 3, 2, 1, like 1, 2, 3. We have like 2, 3, 1, like 2, 1, 3. We have like 1, 3, 2, like 3, 1, 2. It's kind of like this. It has n factorial elements because it's like how many elements are in here? Well, they're all of this form, and so they're all of this form. And it's like, how many elements can you have in the first? Well, you can have like n. Then how many elements can you have here? N minus 1, n minus 2. Having a disconnect between this right now. Oh yeah, I forgot. This is kind of like, you kind of think this out, and okay, it's like a sequential decision process where it's like on the outcomes. So it's like at step 1, you can get 3 different like hats. You could like draw hat 1, hat 2, or hat 3. And so there's like 3 possible outcomes here. And then at time step 2, like this guy, you could do 2 possible. Here you do 2 possible, and here you could do 2 possible as well. So here you could do like hat 2 or hat 3, hat 1 or hat 3, and then hat 1 or hat 2. And then for each of these, you only have 1 possible outcome at this point. So here you have 3, 2, 1, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1, like this. So, and it's like, how many branches are there in this tree? There's like, well, we like start off with n branches in the first one. And so for each of those n branches, there's n minus 1 branches from that. So it's kind of like n minus 1 plus n minus 1 plus n minus 1. Yeah, it's basically that. It's n minus 1 plus n minus 1 plus n minus 1, or just n minus 1 times n. And then for each of those branches, there's n minus 2. So yeah, it's kind of like n. You can kind of think of it like that. Like you start off with n branches, and then for each of those branches, there's like n minus 1. And then for each of those branches, there's n minus 2. So when you're doing this kind of thing, the kind of like product rule, it's kind of like you're implicitly building out this tree, and the product rule is telling you how big is this tree? Like how many paths are there? Like how many leaf nodes are there in this tree? Like this tells you the number of leaf nodes just at n. This tells you the number of leaf nodes at step 1. This tells you the number of leaf nodes at step 2. Yeah, I just think it's really important to have that visualization, what this is implicitly representing. It's like a very compact way to not have to like draw out this whole tree, but like this tree is getting generated when you like do this. The sample space of all possible hat assignments. It has n factorial elements. Yeah, so to kind of connect that, wasn't really thinking of the sample space like this, but yeah, I don't know. It's like let's develop a process to generate all the elements in the sample space. Well, every element is generated by this process. We select the first hat, and in that case, there's three possible choices. There's three possible outcomes. Yeah, there's three possible outcomes for the first. It's a little weird because this is just like one experiment, so there's only one outcome. But if we think about it, if we kind of like informally think about it as three different experiments, then you can kind of say like the first step in this process, there's an outcome, one of three. And then like the next one, there's yeah, two things you can draw. So two and three, one and three, one and two. I can actually just draw it like 1, 2, 3, like this. It's a little cleaner if we don't have probabilities. So then the next one is this. The next one is 2, 3, 1, 3, 1, 2. And then the third person picks their hat, and we get 3, and we get 2, and we get 3, 2, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. So in some sense, this is the sample space. Where each of these branches is one element in the sample space. You have 1, you have 2, yeah. Kind of like that. You have one element here, you have another one like down here. So we say, consider the sample space. It has n factorial elements. Well, yeah, it's like how many elements does it have? Well, then it's like how many branches does this tree have? Which is like how many leaf nodes does it have? And the number of leaf nodes is like we're kind of doing out the tree. There's like n nodes here, there's n minus 1 here, there's n minus 2 here. And to kind of like build out this tree kind of implicitly in math, you kind of like have n nodes, and then for each of those there's n minus 1, so you kind of like multiply that, and then you multiply this, and so that gives you the full tree, and so that gives you the number of leaf nodes, and that's the number of elements that are in the sample space. Okay. Let's see. It has n factorial elements. Okay. So yeah, we're kind of thinking of sample space. That's kind of how we're thinking of the sample space. N hat selections for the first person. Yeah, so you have like n for the first person, n minus 1 for the second person, n minus 2 for the third person. Every single element event with every single element event equally likely. Yeah, I mean, in that case, if you just have like n factorial things, then to like pick any like one out of those, there's a 1 over n factorial chance that you'll do that. Question is to calculate the probability of a single. Yeah, so that's good. Cool. Just gonna take a little note. Okay. This is really great that the little like annotation thing is here in the bottom left. That's like, oh, that's so nice. Okay, part B. The first M persons who picked hats get their own hat back. So in this case, yeah, we can do a little example. So yeah, I kind of want to do it out in the search tree too. What if we have like n is equal, let's do n is equal to, I can't do, I don't think I can do like undo when it's, oh, I can do undo when it's full screen. Okay, I just have to click over here. Maybe let's do like n is equal to 4 and n is equal to 2. The first M persons who picked hats gets their own hat back. Okay. Well, in this case, if n is equal to 4, then like the first person goes and they're like, all right, they could get 1, 2, 3, 4 like this. They could pull hat 1, 2, 3, or 4. Oh, yeah, we want to think about this more in terms of probability. So they could either like get their hat back. So there's n hats right now. So there's basically like a 1 in n chance that happens. And the bad case is there's an n minus 1 over n chance. But let's think in terms of actual like concrete numbers. So basically there's a 1 in 4 chance that they get their hat back. This is a good outcome. And then there's a 3/4 chance that there's a bad outcome. So that's good. So this is like person 1 goes, and now person 2 is going. So down here, there's like 4 hats remaining. And now there's 3 hats remaining. So person 2 goes, and there's 3 hats, so there's a 1 in 3 chance that they get their hat back, and there's a 2/3 chance that they don't get their hat back. And we don't really care about this case. Kind of want to write this out in terms of the probability, what is this event, I guess, but let's just kind of write it out informally. So let's say what's the probability of that person 1? Yeah, hold on. Actually, I'm not gonna do this. Okay. I don't want to do this out. What's the kind of? It's like person 1 gets their hat back, and then person 2 gets their hat back, given that person 1 got their hat back. Recall what is this? We take probability of an event. An event is a set. So what are the potential outcomes of this probabilistic experiment that I'm setting up? So what's the sample space? So oh man, this is great. Just dealing with these primitive things, the sample space. We got these visualizations. This is great. So this probabilistic experiment, I don't know. I could call it what. I don't know. I kind of almost want to think of it in terms of just almost like a continuous event space where. Well, no. I mean, I think the most natural thing would be there's 1, 2, 3, 4, and I'm defining the event 1. No, I don't even know. We could just literally say the probability of 1 like this is equal to 1/4 like this. And I guess we could say 1, the event 1 is equal to 1 like this. Let 1 be the event that 1 occurs. So, and then, we know the probability of 1 complement is equal to 1 minus the probability of 1 is equal to 3/4, like that. And so now this is weird. There's kind of okay. Okay. So kind of, I don't know, with conditional probability, you're kind of transported into a new universe. So the weird thing is, I guess these are different probabilistic experiments, because if I was just going by if these were all the same experiment, I guess it's almost kind of you have 1, 2, 3, and 4. So you'd say, all right, the probability of 1, happens, and then so what's the probability of 2 given 1? So you would kind of think that 1 happened, So like none of this stuff happens. So we're kind of like in this universe and we say, all right, like what's the probability of 2 happening? And we're like, oh, that's like obviously 0 because like this happened. And so there's no way that this can happen. But really kind of like when we say this, the probability of 2 given 1, we actually really want like the complement of that. Like we basically want to say, all right, like this is out, and now we're transported into this universe here. So this is a bit weird. I guess this could be like a new kind of, yeah, like a new kind of thing. Hmm. Hmm. I guess, yeah, the problem is because if we're like just using the definition of conditional probability, then like the probability of A given B is equal to um what are like the different ways to write this? Like A given B, like call that, if we have kind of like two events here, A and B, like what is the probability of A given B? It's like, so B happened. So the probability of A given B is like, we're kind of in this new universe. So like the probability of B is the denominator. Like recall that if we just ask like, what's the probability, like what's the probability of A, for instance, it's almost like you can kind of think of that as that's equal to the probability of A over 1, where like 1 is the, I guess it's the probability of omega. Maybe that's a better way to think of it. Like the probability of A is equal to the probability of A over the probability of omega. It's kind of an interesting way to think about it because it's like this down here is like the universe. This is the universe that we're in, kind of. And I guess if you kind of like actually just did out the definition and you say the probability of A given omega, yeah, that's kind of interesting. Yeah, let's just clear this out. So just like thinking about conditional probability, you have like, we could say the probability of A given omega is equal to the probability of A over the probability of omega. Hmm. And so if you say like and like this is true because, yeah, like this thing is 1. So always, so you say the probability of A given B is equal to, recall if we have like omega, we have like A, we have B. So B happens. So yeah, our new universe is the probability of B. And yeah, so basically we're in this new universe and we just want like this little bit here over the probability of B. It's like the probability of A intersect B. Just can kind of like do this. So now we're kind of thinking about like repeated, not even repeated, like we're just thinking about conditional probability right now. So we kind of like have to draw this picture. Like so we're talking, so conditional probability is defined within the same sample space where, basically like A is a subset of omega and B is also a subset of omega. This is how conditional probability is defined. So when we said, like the probability of 1 given 2, and we had our sample space of, I guess, like 1, 2, 3, 4, like this. When we said 2 happened, so we're kind of in this space, or like we said, the probability of like 2 and 1. So let's just do 2 and 1. So the probability of 2 given 1. So it's like this event happened. But we don't want that to be the case. Like, yeah, so we just have to like redefine kind of like what these events are. So interesting. So it's almost like you want to let the event 1 be equal to the event 2, 3, and 4. But no, because that kind of goes opposite with like these are all the different outcomes of the experiment. I guess the only way to really I feel like the only way to kind of reconcile it is you kind of have to make these different probabilistic experiments with like different sample spaces. I don't know, because I do want the intuition where we kind of start off with the sample space and then we kind of like cross this out. We don't say that we're in it. But it kind of goes against the, like, just to keep writing this out, say let 1 equal the event 2, 3, and 4. Yeah, I guess we can just go down this route. So if we say like, all right, like 1 happens, like what's the probability of 2 given 1? But yeah, but the outcome that we got is 1, and that outcome isn't actually in here. With replacement, without replacement. So maybe we can ask ChatGPT. Let's see. Maybe we can just copy this. I want to write out part B in terms of a sequence of products, like probability of 1. Wait, what even is the probability of 1? I guess I guess the probability of 1 means like the first person gets their hat back, and like the probability of 2 given probability of 1, probability of 3 given 1 and 2. I'm having trouble defining the probabilistic experiment in terms of omega and events, sets, and outcomes. I want to say let 1 be the event where person 1 gets their hat back at number 1. But then when we say probability of 2 given 1, that would be kind of impossible, because just applying rules of probability, we are in event 1, so event 2 is impossible. It's almost like I want to define the event 1 to be the set 2, 3, 4, so we can continue to go deeper into the conditional universe of the hats that remain. But going with the definition of probability, we want something like the event 1 to be 1, because that's the outcome that we want in the event. So these two things are at odds. Can you help me reconcile them? Reducing the sample space as we fix certain outcomes. Okay, so we think in terms of permutations. Okay. Oh, wow, interesting. Okay, so maybe this is the way around it. When you have like a sequential thing like this. Oh wow, yeah, man, that's fucking it. Yeah, because it's like you really want it to be kind of more like this, where you've got all the potential we've got all the potential outcomes, like 1, 2, and 3, and like 1, 3, and 2, and yeah, 2, 1, and 3, 2, 3, 1, 3, 1, 2, 3, 2, 1, like this. So we want to actually say the probability of 1 is equal to it's basically this. It's like these first two. Or I kind of want it to be like reverse. Like this is, it's actually this. So it's like the probability of 1 is equal to, 1, 2, 3, 1, 3, 2. Then we say the probability of 2 given 1. 2 given 1. It's equal to the probability of 2 and 1 over the probability of 1. So yeah, we're kind of like in this space. So this is the only outcome that is good at this point. Well, okay. And it's kind of interesting. Like the probability of 2 is equal to so 2 goes second and they get their hat back. So it's basically like this event here and this event here. It's like these two events. So when we just compute the intersection of these two sets, basically like this is the only set, that actually survives the intersection. So probability of 2 given 1 is equal to, so the intersection is just, it's just 1, 2, 3 over the probability of 1 was yeah, it was like this initial set here. So yeah, so that's equal to 1/2. And then we say the probability of 3 given 2 and 1 is equal to the probability of 3 intersected with like 2, 1, 2 and 1. 2 and 1 like this. Over the probability of 2 and 1. So 2 and 1 was just this. And probability so the probability of 3. So the probability of 3 is equal to person 3 gets their hat back. So it's this event and this event right here. So like this guy and this guy here. So the intersection between this and these two things and just this is equal to, yeah, it's just the probability of 1, 2, 3 over the probability of 2 and 1. Wait. Oh, yeah, it is just 1 because yeah, it only left this case here. 1, 2, and 3. That's right. So yeah, it's kind of weird to think about, like if we kind of set it up, we got, like the sequential thing we want is like the probability of 1 times the probability of 2 given 1 times the probability of 3 given 2 and 1 times the probability of 4 given 2 and like we'll go probability of 1 and 2 1 and 2 and 3, like this. The probability that the first person gets their hat back, that's kind of like a whole bunch. It's like that. And then the probability of 2 given 1, kind of like maybe cut off like half of those. And the probability of 1 and 2, we cut off like that half. And the probability of like 1, 4 given this, and we're like just left with this. This is like always just 1 at the very end. So if we wanted to kind of draw it in that grid from before, maybe we can draw it in terms of not a grid, but more like this kind of thing, where we have kind of like 1 and 2 and 3. So it's like the probability that 1 gets their hat back. It's like 1. Yeah, these aren't all distinct. We can't think of them in terms of distinct. It's like 1 and 3, 2, and yeah. So I guess this is kind of like a key point. Like when you think about a sample space where there's like repeated kind of draws, it's like a sequential thing. You need your outcomes to be these like sequential like tuples. If you do want to have that set behavior where you are kind of like conditioning further and further into probabilistic universes where you just keep kind of like crunching down and down and down and getting smaller and smaller and smaller, and like but keep like blowing up the conditional universe to like crunch down, but then like blow that up to your new conditional universe, and then crunch that down, and then blow that up into your new conditional universe. So I think it would be actually cool to draw that out, because so 1, 2, 3, so there's 6. There'd be 6 possible things in this conditional universe. What's a good way to draw that? I can think of a 4x4. I don't know about 5. 1, 2, 3, 4, 5. I guess we can just kind of draw it like as rows. Not even that. Let's just start doing this. 1, 2, 3. 1, 3, 2. 2, 1, 3. 2, 3, 1. 3, 1, 2. 3, 2, 1. So these are these are the outcomes of our experiment, probabilistic experiment. Okay, so I guess we say, all right, like one happens. So these are basically all fucking gone. Like, and now we're in this universe right here. Maybe a better way to do it is we're in this conditional universe right here. No, let's actually do it in terms of, yeah, it's like we're in this. Like this is good. This is where we are. So that happened. So now we say probability of 2 given 1. So we're kind of conditioning on this, and like what subset of this is 2? Well, it's basically like what's the intersection? It's basically just this guy right here. And now we say, all right, what's the probability of 3 given 1 and 2? 1 and 2, so we're just in this universe here. So the probability of 3 happening, that is like this one right here. It's like still the same. I don't want to do it in terms of maybe just like the crisscross things. Okay, so the crisscross things, like the probability of 1 is like this, right here. And then the probability of 2 given 1. So we're in this universe and we're just computing the overlap of, 2. So we're basically just here. And then we say the probability of 3 given 1 and 2. And so, yeah, that intersection is just this right here. So anyway, I'm gonna go grab some breakfast. That was a pretty cool diversion. It's like amazing that ChatGPT can help me get that insight and understand that. So, all right. Thanks, guys. See you later.